Welcome to notes 9.1 through 3. These notes kick off our unit on transformations. And you should be pretty familiar with transformations already because you learned about them in middle school. So some of this will be a review, some of it will be new, but none of it should be too difficult. And we are going to begin our unit with talking about translations and reflections. And so a transformation is simply an operation that changes a geometric figure in some way to produce a new figure. Okay, and translations are a type of transformation. They are a transformation that moves every point of the figure the same distance in the same direction. An isometry is a congruence transformation. In other words, any transformation in which the figure and the figure it's transformed into are congruent, that is called an isometry. And then we have pre-image and image. The pre-image refers to the original figure, and the image refers to the transformed figure. So we can express a translation's distance and direction as a vector. So here we have our pre-image, RST, and then we've moved every point the same distance in the same direction. And that's what a vector is. A vector has a direction and it has a magnitude. And then we wind up with R prime, S prime, T prime, which is our image. So then when we add that little apostrophe to the terminal point, that's called prime notation. And it indicates that our figure has been transformed once. And then if we added a second one, it would be double prime, and that would mean we had done 2 transformations to our figure, and so on. So the notation that we use in vectors, it looks something like this. And it looks like it's an ordered pair, but it's got these little pointy brackets on either side of it. And what that means is that the X in that set represents the horizontal change and Y represents the vertical change. So in looking at our problem here, it asks what the translation vector is from M to G. Well, we have to look at the horizontal change first, and so that is this distance right here, and I went from -3 to +6, so that is a change of +9. I moved 9 to the right, and then my vertical change was from +6 down to +1, so that was a change of -5, or 5 down, and that is simply my translation vector. And then we have something known as a composition of 2 translations, where you take the 2 translations and you add them together and you get a single translation. So for example, if I had a vector of 3, 6, so I moved 3 to the right and then 6 up, and I followed it by moving 5 to the left and 8 up, then I could just add the x coordinates together. 3 plus -5 gets me -2. Add the y coordinates together, 6 plus 8 gets me 14. And this vector right here has the same effect as these 2 vectors together. So this is called a composition. For some reason, students forget this. I guess because it's so basic and so easy. So please go ahead and make a mental note right now that you're not going to be one of those students who, when faced with a very simple problem like this on the test, completely draws a blank. Okay, so now we're going to have just the briefest of introductions to matrices. And a matrix is nothing more than a rectangular arrangement of numbers into rows and columns. And we can use matrices for various things, including to translate figures on a coordinate plane. Now, you're going to learn a ton about matrices in Algebra 2, so we're not really going to spend a whole lot of time on them, but I'll just kind of quickly show you how you can use them to do a translation. So we are supposed to write a matrix to represent triangle RST, and we're given the vertices. And in matrices, we have rows, which go across, and then we have columns, which go down. And in this case, my columns represent the points themselves, and the rows represent the x coordinates. So I have a row for the x coordinates, and I have a row for the y coordinates. So I'm just go ahead and write my points. So I've got the point -5, -4. The point S is -1, 2. And the point T is 3, 1. So that is my rectangular array of elements. And then it wants me to translate this triangle using the vector -4, -1. So I'm going to shift every point 4 to the left and 1 down. And we're going to use a translation matrix to do that. And again, remember that this represents X and this represents Y. And since I'm translating a matrix that has 3 columns, my translation matrix also needs to have 3 columns, and then obviously it needs to have the 2 rows for the X and Y. So I've got my -4, -1, and I'm going to put that in each column so that when I add these 2 matrices together, they have the same number of rows and columns, because when you're adding matrices, the number of rows and columns must be the same. So I'm going to rewrite my translation matrix here, -4, -1, -4, that's a -4, -1, -4, -1, and then I'm going to write my polygon matrix, which was -5, -4, -1, 2, 3, 1, and then I'm going to simply add my corresponding elements. So top left gets added to top left, and it goes in the top left, and so on. So -4 plus -5 is -9, -1 plus -4 is -5. -4 plus -1 is -5, and -1 plus 2 is 1, and -4 plus 3 is -1, and -1 plus 1 is 0. So that gives me the point R prime, which is now -9, -5. The point S prime is now -5, 1, and the point T prime is now -1, 0. Was that the most efficient way to go ahead and to do this process? No, it certainly wasn't. I mean, obviously you could have just taken every point and added the translation vector to the point without having to go through this whole matrix process. But we just wanted to kind of show you what a matrix was and how it could be used in translations. Now we're going to go ahead and do that process on the graph. So I'm going to graph my original, which was what, -5, -4, so that was R. And then S was -1, 2. So that was S. And then T was 3, 1. So that was T, and draw my triangle. And you can tell whether we take every point and count 4 to the left, so I'm going to do S here, 1, 2, 3, 4, and then 1 down, right? And that gets me S prime. So my new coordinates for S prime are -5, 1, which is the exact same thing I got when I actually did my translation. So you can either count it on the graph or you can do it with the matrix, and you should always get the same exact thing. I'm going to go ahead and assume that you can translate the other 2 points that same way, and we are going to move on to talk about the properties. So the 2 properties of a translation are that it's an isometry, meaning when I slide that figure all over the place, it's not going to change the size or the shape of it. It's still going to be congruent to the original figure, and also the same orientation. So what that means is that, for example, on our figure here, you'll notice that S and T is clockwise to S. Well, on my figure, that is transformed, T prime will still be clockwise from S prime. It's not going to change that in any way. These properties are important. You're going to need to know the properties of the kinds of transformations that we talk about in this unit for the test. Okay, now we're going to move on and talk about reflections. And a reflection is an operation that exchanges all points of an object with its mirror image. And then whenever we have a reflection, we have a line of reflection, and the line of reflection is simply the line that is equidistant from the points in a figure and the points in its reflection. When we talk about the properties of reflection, they are isometry and change in orientation. It's isometry because the size of the figure does not change, but when it's reflected across the line of reflection, we do have a change in orientation. So points that were once clockwise are now counterclockwise, and vice versa. Okay, you can see that with my two stars right here, because the one on the right, I have points A and B, and then I have my line of reflection in between them. Well, A prime will be this one, but B prime will be this one. So now what was clockwise is counterclockwise, and that's how you can understand that there's a change in orientation. Okay, so now we have triangle ABC, and we need to graph it first off. So we've got the point 1, 2, and we've got the point 3, 0, and then we have the point 5, 3. So this one is A, and this one was B, and then this one is C, and we connect the dots. And then it asks us to graph the reflection across the line x equals 2. Well, the line x equals 2 is this line right here. It is a vertical line, obviously at x equals 2. And so the way we're going to graph this is we are going to count every point, how far away it is from the line, and then we can count that many across. So A, for example, it is 1 away from the line, so I count 1 across it. And that new point, that is going to be A prime. And that is the point, let me see, what is that? That's the point 3, 2. And then same thing for B. B is 1 away, so I count 1 beyond it, and B prime goes here. So that is the point 1, 0. And then C prime is 1, 2, 3, so I count 1, 2, 3 beyond, and that is C prime. So C prime is now at -1, 3. And then I connect my points. And that's as simple as it is. You probably are used to reflecting across the x and y axis and maybe not so much another line, but you need to get used to that. The most difficult part of reflection is just remembering that x equals lines are vertical and y equals lines are horizontal, and that's really not all that hard. All right, I'm going to let you do B all by yourself, and then you're going to give me some of those answers in the notes check. Okay, so final problem for today. We have the endpoints of CD are -2, 2, so -2, 2, there's C, and 1, 2, there's D. So C, D, line segment. And it wants us to reflect the segment in the line y equals x. So you can either do this on the graph, or I'm going to show you a couple other ways that you can think about this. So if we do it on the graph, we need to begin by actually graphing the line y equals x. Well, it is the line that goes to the origin. It's the parent function, right? So, and it has a slope of 1. So it's going to go through all of these points here. So let's see if I can do that. Almost. All right, so that is the line y equals x. And then if you want to do this graphically, you just count to that line and then change 90 degrees and count beyond. So for example, D here. D is 1 away from the line, so I count 1 perpendicular to it, and that gets me D prime. C, I can count maybe down to the line, so 1, 2, 3, 4, and then I turn and I go 90 degrees and I count 1, 2, 3, 4 beyond it. And that is C prime, and I've graphed my new figure. But you can also do it just by thinking about what it means to graph across the line y equals x, or reflect across the line y equals x. It means that every y value becomes the x value and every x value becomes a y value. So basically these two just switch. So for C prime, I wind up with 2, -2 by switching my x and my y values, and you'll notice that that's what, in fact, where we graphed C prime. And then D prime, when I switch these two values, I wind up with the point 2, 1, and that is in fact where that wound up. So you can either do it by thinking about it algebraically or by doing it on the graph. One thing I do want to point out, though, and this is very important, and you should really be paying attention right now, and that is that this line of reflection is the perpendicular bisector of the segments joining my point and its reflection. So for example, this line that joins D to D prime, my red line is the perpendicular bisector of it, or the segment that joins C to C prime, which I drew terribly, that red line is the perpendicular bisector of it. And the reason why that's important is frequently I'm going to give you a point and its reflection and ask you to write me the equation of the line of reflection. And so we know that perpendicular lines, they have opposite reciprocal slopes. I can't talk and spell reciprocal at the same time. Opposite reciprocal slopes. And then we know that since it's a bisector, this is a midpoint, and we'll have a slope and we'll have a point, and we'll be able to write the equation of the line in y minus y1 equals mx minus x1 form. Remember your algebra? Okay, so line of reflection is the perpendicular bisector of the segment joining a point and its reflection. I can't emphasize that enough, and that's probably the most difficult concept in this section, and it's really not all that difficult, so yay. All right, so that's all I have for section 9.1 through 3. Be sure to do the notes check, and I will see you in class. Thanks.